typically talk about science and scientists, what we really imagine often is someone in a white coat, like a lab jacket, with goggles on and safety gloves. Or no, maybe we think of someone at a desk running a model simulation or seeking highly complex analytical solutions using high-powered software. But I'm actually a soil and water scientist, so the equipment that I reach for in the morning are actually something like this, a soil auger, and of course a decent pair of welly boots. You see, I'm working with the Irish Agricultural Catchments Programme, and our job is to evaluate and really to find out what are the driving factors controlling our water quality. And we do this so that we can help to achieve EU objectives to maintain clean, good quality drinking water and to safeguard our future. And as part of this team, I've been working in our 6 study river catchments. And these are essentially areas in which we have developed a natural outdoor laboratory in which we run our experiments. So rather than have a very contained environment isolated from the wider environment and the other factors which control how our soils, our crops and our water behave, we have a really grasp on reality because these are catchments which are very special. They're not just for research. Actual, genuine farmers and real people are living in these catchments. Pardon me. There we go. And we're taking water samples in these catchments from the outlet of the rivers, and we have automated machinery that take water samples every 15 minutes. This gives us a really high temporal resolution, and these machines are running 24 hours a day, 365 days a year. And we couple these water quality monitoring with investigations of the soils of the area, because soils really play a critical role in controlling the transport of water and nutrients to our water bodies. You see, the physical and chemical characteristics of the soils themselves dictate whether they hold onto or release chemicals or nutrients. And if we take account of this, we can design better policies and better management practices to safeguard our water quality. So let's take an example. In freely draining soils, these soils are full of pores. They're essentially a lot like a sponge. So water and nutrients can flow through those pores. And let's take the example of a particular nutrient. Let's talk about nitrate. Nitrate is a mobile nutrient. So when it gets in solution in water, it can flow through these pores. And let's take, for example, thin soils in which there's not a lot of sponge there to hold on to the nutrient. Or let's take karst environments. Think back to your Leaving Cert geography folks. They're very hollow. They've got big tubes through which the water can travel. In these instances, nitrate can travel quite rapidly through the soil, or through, we call it the unsaturated zone because it's not full of water the whole time, to the groundwater below. And if we take account of this, we can either devise strategies to limit nitrate loss in quickly draining areas, or alternatively, we can predict timelines in the slower draining areas as to how slow that's going to be. Let's consider a very different contaminant. Let's talk about phosphorus. This is the limiting nutrient in surface water, so really it's the control on whether we get eutrophication, that's algal growth, or not. And phosphorus is very, very different to nitrate. Phosphorus is sticky. It likes to cling on to clay particles. You can think of clay particles a little like the lint roller of the environment. They're flat particles and they hold a negative charge, so things tend to stick onto them. So you think, oh, well, maybe that's a good thing, and sometimes it is. But in our heavy soils, that's soils which are draining very, very slowly, if you get a heavy rainfall event, those particles can be lifted from the soil surface and physically moved to our water bodies. And any contaminants or potential contaminants such as phosphorus, which are sticking to those particles, will move along with them. So if we know and understand our soils, we can supply these nutrients. These nutrients are not a bad thing, they're actually a great thing. They're what we need to promote crop growth. So if we understand our soils, we can apply these nutrients at the right time, in the right way, and in the right place to optimize crop production. And this has agronomic, economic, and environmental benefits. It's a win-win-win. Now this year, my particular mission was to examine the water quality or the water chemistry in our study catchments, not just at one point as we do every 15 minutes, but across the entire main stream and all of the tributaries and all of the major ditches. It was a really big endeavour, and essentially it involved getting the boots on. I didn't have a soil auger on those days. I had a water sampling bottle and a probe which allowed me to measure temperature, pH, oxidation potential, a whole range of parameters. And we did something, me and my team, something which was really quite impressive. These things are called synoptic surveys, which means you get eyes on all parts of the catchment or the water body. And to date, in English catchments, they did parallel similar studies, and they averaged out maybe 1 to 2 samples every kilometre, sometimes less. What our agricultural catchments team achieved was 5 samples per kilometre over 15 kilometre square catchments, and we did this in 4 of our catchments and 3 times. So we were well tired of it by the end of fieldwork, but we got a vast amount of data from this. And what we saw from this already has been very, very interesting. In most cases, we were able to relate the nutrient concentration in water to things that we knew about, to things like soil type, to management practices, to weather. But in certain cases, we were seeing nutrient, phosphorus specifically, concentrations that were higher, and we couldn't immediately draw conclusions as to why this might be. And what was really interesting is that in addition to the nutrient concentration, we were seeing microbiological indicators as well, and we examined these with colleagues in NUI Galway. So where was this mystery phosphorus coming from? Well, I'm sure all of your houses, and probably almost every house in Ireland, has a flushing toilet. And what happens after you flush that toilet? Well, the waste either gets washed into public sewerage, in which case it goes to wastewater treatment facilities, or it goes to a septic tank. Now, septic tanks, much like our agricultural soils, take advantage of inherent properties of the soil in order to remove nutrients but allow water to flow. Essentially, septic tanks have a leaching area, in which case the soil acts as a filter, and we take advantage of those Velcro-like properties to hold on to the nutrients. But if septic tanks are perhaps poorly installed or not correctly maintained, those nutrients build up in the soil until it reaches capacity, until the clay particles and the organic matter particles can only hold on to so much, and after that, those nutrients are free to be transported through the soil to ditches, streams, and rivers, and we don't want that. So this is really a great exercise in learning how our soil interacts with our water quality and what a great role it is playing in all of that. So whether you're a farmer applying fertiliser to boost production, or whether you're just a resident going about your day-to-day business, if you appreciate how our soils work, we can work with them. And it really has far-reaching implications for all of us. I think they're quite obvious implications in terms of our water quality. But really it shows that soil isn't just dirt. In fact, it's actually very far from it. Thank you very much.